This is chapter 15 for AP Chem Review on acids and bases. To begin with, there are several definitions of acids and bases to be aware of. First one's called the Arrhenius definition. Arrhenius definition is that acids make hydronium ions in solution, bases make hydroxide ions in solution. The second one is the Bronsted-Lowry, or sometimes I've just seen it as the Bronsted definition. Acids donate a proton, bases accept protons. And finally is the Lewis definition, which acids accept electron pairs and bases donate electron pairs. If you look over at the board, I have an example for the acid definition for all three. First off, HCl is hydrochloric acid. If I have hydrochloric acid in water, H2O, it can make hydronium, H3O+, and then the chlorine ions. So that follows the Arrhenius definition in that it's able to make hydronium. Bronsted-Lowry is donating a proton. Well, if you notice, HCl will give its H to water to make hydronium. So this also follows the Bronsted-Lowry definition because it's donating a proton. Lastly, acids accept electron pairs. If I really drew the mechanism out for this, what happens is this pair of electrons on the oxygen is going to take the hydrogen away from HCl. Then this bond, which was 2 electrons, is going to be just for the chlorine, which is going to end up giving you the Cl- over here. So all three definitions work for how that can be an acid in that particular case. Next thing we're going to go over is the mechanism for conjugate acid-base pairs. I already gave you the example of HCl and water, but we can draw that one again here in a second. And then after that, I'm also going to give you a couple other examples. I'm going to give you a base example, like ammonia in water. And then lastly, I'm going to give you an example of water self-ionizing. So if we start with the HCl example, here's HCl plus H2O, dissolved in water. Once again, it's going to make hydronium and Cl-. In this example, the HCl is the acid. Water is actually going to act like a base in this example because it's accepting a proton, donating electron pair. The hydronium is what's referred to as the conjugate acid. The chlorine ion is what's referred to as the conjugate base. Second example I'll give you is of a base, ammonia, NH3. If I put NH3 in water, my double arrow, if you don't recall from the equilibrium chapter, means it's going to be reactants and products both made here, is going to give me hydroxide polyatomic ion and ammonium. In this case, NH3 is not donating hydrogen, it's accepting one, so it acts as the base. Water is going to act like an acid in this example. OH we should always recognize as the conjugate base. And then the ammonium polyatomic ion is the conjugate acid. The very last example to show you is the self-ionization of water. H2O plus H2O makes H3O plus OH minus. In this example, one water is going to act like an acid, the other one is going to act like a base. Hydronium then will be the conjugate acid. Hydroxide will be the conjugate base. When we even have distilled water is not pure water because water will self-ionize. Now only to a small extent, but that self-ionization of water is very important when we get to the next thing, which is going to be dealing with what the pH scale is. To begin with, pH stands for power of hydrogen. So if acids are what make the hydrogen or give the hydrogen, that's what's referred to as. Now the pH scale is based off of water. As you will learn, that the pH scale normally goes from 0 to 14, but you can exceed 14. You can actually be in the negatives as well. So it's not as simple as it's always 0 to 14, but it's based off of water for that. Equations to know is first off the Kw, the equilibrium constant for water, equals the hydronium ion times the hydroxide ion. Now, if you recall from equilibrium, we could have that divided by water as the reactant on the previous slide's equation for self-ionization of water, but water doesn't factor in equilibrium constants. So the Kw is 1 times 10 to the negative 14. The other equations we need to be aware of is pH equals the negative log of the hydronium concentration. So if I know the hydronium concentration, which for a strong acid is its molarity, I can just plug that into negative log of this equals the pH. On the other hand, if I know the pH and I want to know the molarity of the strong acid, or the hydronium concentration, it'd be 10 to the negative pH to give me that. Something that we're not as familiar with as early chemistry students is something called pOH. This is what measures bases. So pH really is a measure of acids, but we can convert that over to measure bases as well. The pOH is the same as the pH, the negative log of the molarity if it was a strong base. Vice versa, again, 10 to the negative pOH equals the hydroxide concentration. An equation that will be very useful though is going to be pH plus pOH equals 14. So if you have a base, the molarity is the hydroxide concentration, I can solve for the pOH and plug it into here to figure out that last part. Here is the equation that we're going to work on here. It says blood has a base concentration of 2.5 times 10 to the negative 7th. What is the pH of blood? So if we go over to the board here, the first thing that we want to do is note that the hydroxide concentration is going to equal 2.5 times 10 to the negative 7th. What I can do is solve for the pOH. When I solve for that, I get 6.60. But pOH is only used with bases. It's not really used as an overall indicator of is it an acid or is it a base, recalling that below 7 is an acid, above 7 is a base. So what I need to do then is pH plus my pOH, which is 6.60, equals 14. That will get me a pH of 7.40, which if you check on your slide is the correct answer. So once again, if you have a base, remember to use the pOH part first, then what you can do is you can solve for the pH from there. The next topic we're going to bring up is strength. Acids and bases have different strengths associated with them. For example, hydrochloric acid is a strong acid. What that means is if I put that in water, it will completely dissolve to make the hydronium ions, and in this case the Cl- ions. So some acids or bases, when you put them in water, will completely react with water. Weak acids only partially dissociate in water. An example there would be acetic acid. The same thing can be said for bases, and once again what I'll do is I'll show you an example of a strong base like sodium hydroxide and a weak base like ammonia. So to begin with, a strong acid like HCl, I've shown you this equation a few times already. HCl plus H2O will make hydronium plus the chlorine ion. That's a strong acid completely dissociating, hence it's showing one direction. On the other hand, acetic acid, which is HC2H3O2, that plus water will only partially dissociate, hence the double arrow into the hydronium, so it still makes the acid ion, and C2H3O2 minus. Strong bases, now be careful if you look at the base. Sodium hydroxide is an ionic compound. So technically when we draw an ionic compound, we draw water over the arrow because it's dissolving in water. So how this makes the hydroxide is it just breaks the positive and the negative apart. I'm left with Na plus and OH minus. Arrow only goes in one direction because sodium hydroxide is a strong base, so it will completely dissociate to make hydroxide. And once again, since it's an ionic compound, metal and non-metal, it's just going to break apart in water. As opposed to ammonia, the last example, NH3 plus H2O only partially dissociates to make, once again, the hydroxide polyatomic ion. And in this case, the ammonium polyatomic ion. You'll actually oftentimes see ammonium hydroxide, which again is NH4OH. You'll see that oftentimes to represent the same thing as ammonia dissolved in water. Now the easy calculation we went over a little while ago was calculating the pH of a strong acid or base. That's not tricky, that's the negative log of the hydronium. What's more difficult is calculating the pH of a weak acid or base. Now this is the same thing that we did with equilibrium calculations in the previous chapter. So you can always look back at that and note that we have to do the ICE method. So in other words, if I had an acid dissociated in water to make hydronium and then the acid anion, my Ka would end up being the products divided by the reactants. What I have to do from there is then use the quadratic formula. So we're going to do a sample problem right here. What is the pH of, and that should say, a 0.122 molar monoprotic acid whose Ka is 5.7 times 10 to the negative fourth. I usually like to start with just the generic equation of here's my acid plus water. It's a weak acid. It's going to make hydronium and A minus. Initially, I'm given 0.122. Now the nice thing about this as opposed to equilibrium equations, if you recall from the equilibrium chapter, you could have both reactants and products and have to solve for Q first to determine the reaction direction. The reaction is always going to go in this direction, left to right, which means my change then is a negative X. The acid's going to lose a certain amount, which means I'm going to gain a certain amount of hydronium and the acid anion. So at equilibrium, 0.122 minus X will be my concentration of the acid. The hydronium, which is what we really need to solve for, is going to be X, and this will be X. Going back to the slide, it said take your hydronium and your acid anion divided by the HA. So if I do that, I have X times X, which is X squared, over 0.122 minus X, and that's going to equal the Ka, which in this case is 5.7 times 10 to the negative fourth. If you recall from what we did earlier in the last unit, we then have to multiply both sides by this to get it all by itself, get everything on one side set to equal to 0. So I'll do all that math for you right now. This would be the same as X squared plus 5.7 times 10 to the negative fourth X plus 6.9 times 10 to the negative fifth equals 0. 6.95, sorry. Now, if you get to this point, you can use the quadratic formula. Negative b plus or minus the square root of b squared plus 4ac divided by 2a. You could do that if you wanted to, or instead, there's a quicker way to do it. When we have a small Ka, so once again, small Ka means anything a lot smaller than 0. If it's small like this, that means the acid is not going to dissociate much. So if it's not going to dissociate much, an assumption we can make, and this is what the textbook says, is an assumption we can make is with this value right here. 0.122 minus X. If the amount that you lose, the change is very small, you can assume that 0.122 minus X is basically the same as 0.122. So that's the assumption that the textbook discusses when dealing with a Ka that's small. We don't introduce that to you with equilibrium in the previous chapter because there you get equilibrium constants that are above 1, and there you cannot make that assumption. So some students always just use the quadratic formula because they don't trust when to use that assumption, but if your Ka is several powers to the negative, you should be able to use that assumption. So what I'm going to do is change this to now X squared over 0.122 equals 5.7 times 10 to the negative fourth. Now what I'm going to do is multiply both sides by 0.122. That will get me X squared equaling 6.95 times 10 to the negative fifth. Get X by itself by taking the square root of both sides, and that will have X equal 0.00834. We have figured out the hydronium concentration at equilibrium. We are not done with the problem yet, because there's one last step that we have to do. we now have to take pH equals the negative log of the hydronium. So if I plug in 0.00834 into that, I would get 2.09 as my pH. So once again, the last thing I know is that that shortcut usually works out well, because within the shortcut, you are dealing with small Ka's. Now, if your Ka or your Kb, if it was a base, is a number close to 1, so like a 10 to the negative first power, 10 to the negative second power, then you probably aren't going to use that shortcut. But 10 to the negative fourth, if you understand logarithm dealing with a power of 10, that change is going to be very minimal. Percent ionization is the next thing brought up. Percent ionization is the ionized acid concentration at equilibrium divided by the initial acid concentration. If we go back to that previous problem we just had, the ionized acid concentration was the hydronium ion concentration. So for that, that would be the 0.00834 number. We would divide that by the initial concentration, which was the concentration of the HA to begin with, which in the problem we just had was 0.122. If you multiply that by 100, it will tell you the percent at which the acid ionized by, which once again means how much did it dissociate by. On the board is me showing how to solve for that. Once again, this was the hydronium, or the H+, you might see it referred to as. This was the initial HA concentration. So this is how much acid was created from the initial acid part. 6.8% is my ionization then. The next thing we have to go over is what's referred to as polyprotic acids. Poly means more than one, protic means proton. So an acid that can donate more than one proton or more than one H. Sulfuric acid and phosphoric acid are both good examples of this, because sulfuric acid is H2SO4. Phosphoric acid is H3PO4. So what I'll show you on the board is the sulfuric acid example of how that dissociates. H2SO4 to begin with, sulfuric acid, dissolved in water. Now sulfuric acid, again, you don't know it off the top of your head, but I do, that this is a strong acid, so I'm just drawing an arrow to the right. We'll make hydronium plus hydrogen sulfate ion. That hydrogen sulfate ion, though, still has a hydrogen on it, so that can now dissociate as well in water. Now this one I know is weak, so I'm going to draw the double arrow, but it will make more hydronium and then the sulfate polyatomic ion. Now we could do this with phosphoric acid as well, where it's H3PO4 plus H2O making hydronium, then H2PO4 minus, then H2PO4 minus plus water makes hydronium, HPO4 minus 2, and do it a third time as well, but that's a little bit more than what we should have to be able to do. One of the things we should be aware of, though, is we might have to solve for the pH of a weak polyprotic acid. And this is tricky, because as you saw on the board a second ago, there's two equations you have to abide by. So what's going to happen is you're going to be given a Ka, an equilibrium constant, for each equation. So in other words, you're going to have to do the ICE method, products divided by reactants, and you're going to end up solving for the X value for the first version, for just the first dissociation of hydrogen. Then you have to do the ICE value for the second set as well. Usually the approximation works very well for this, so you don't have to worry about doing the quadratic formula, especially on the second step. But at the same time, there's a lot of math to do with that with the polyprotic. A little too much for me to go over on the board right now, but that is it for Chapter 15, Chain Review of Initial Acid-Base